Okay, let's start with the introductions, and then, yeah, people can join in throughout the session as well. So first of all, hello everyone. Good morning from Vancouver. Now that I see that everyone is joining from different time zone, this is really exciting. So good morning definitely does not suffice. But good morning from Vancouver. Welcome everyone, and thank you so much for joining us today. So my name is Rushali, and I'll be your host. Before we get started, I just want to start with a couple of quick notes. So today's session basically is being recorded. We will also have a Q&A session at the end. And yeah, you can use the chat box at any time for the questions. But preferably, if you like put your questions in during the Q&A session, that would be great. So for today's session, let's introduce our speaker. We have Bryan Stillwell, Ceph Solutions Architect at Clyso, with over a decade and a half years of experience in the Ceph community. So yes, over to you, Bryan.
All right. Well, welcome everyone. So today I'm going to go over erasure coding and the FastEC benefits that Tentacle brought to us. So here's a quick outline. First, I'm going to start off with how erasure coding works and why it's historically been slow. Then I'll dig into the specific improvements FastEC brings in the Tentacle release, and then kind of cover what it unlocks, what it doesn't, and then, maybe some migration paths you could take if you want to switch over to FastEC. So I think it's best to start with 3x replica because it's by far the easiest to understand. It's the way writes actually work is the client initiates a write. The write goes to the primary OSD, and then the OSD goes and replicates to the two secondary OSDs. So, it's not like, the client writes to all three at the same time. The primary is in charge. Here's kind of a quick example of how like a 4+2 erasure coding would work. So the client, initiates write again, goes to the primary OSD. Then the OSD shards the data, calculates parity, and writes it out to the 6 OSDs that it needs. But there was actually I don't know. I guess I kind of understood how this worked a little bit before I started this talk. And I always thought, say if you were going to do like a 4 megabyte write from the client, it would go to the primary. It would divide it up into 4 1 megabyte chunks. The first megabyte would go to the first OS shard. The second megabyte would go to the second shard, and so on. But that's not actually how it works. So here's kind of like a quick example of maybe like a 20 kilobyte file where each one of these is like a 4 kilobyte chunks. This one consists of all A's. This one consists of all B's, C's, D's, and E's. So the primary does split it up, but it does it at 4 kilobyte boundaries by default. That is configurable, which we'll see later. But so what it would do is it would take the first 4 kilobytes, write it to OSD 170, and then 283, whatever. But then you'll see actually this is a good way to explain what a stripe is. So a stripe is 4 kilobytes spread across the K equals 4 OSDs. So a full stripe is 16 kilobytes. But the way Ceph does it is it'll take any stripe that is incomplete and fill or pad the rest with zeros. Then it'll go through and it'll create, calculate the parity or the erasure codes to be able to do recovery. So this is a lot like RAID 6, but it uses Reed Solomon Vanderbond as the erasure code the majority of the time. So why has it been slow? Ceph, when you want to go and do say a sub-stripe read, you want to just read 4 kilobytes from this file at this offset, you just want to read all the Ks, it'll actually go through and read the full stripe. The primary will read the full stripe, so it'll read from all 8 OSDs in a 8+3 erasure code just to serve back the 1 4 kilobyte read that you wanted in the first place. It also pads the objects. So like say if you only wrote 4 kilobytes in an 8+3 erasure code, it actually ends up writing 44 kilobytes. So it'll write 7 4 kilobyte chunks in each of the OSDs of just zeros, and then it'll do another 3 for the parity. So it's a total of 11 4 kilobyte chunks for 44. So it's big write amplification, at least with small objects. Then it has a problem where it's like it's a read modify write. So if you were going to say, modify this chunk here that doesn't have anything, it's just 0 padded right now. So you want to replace that with 4 kilobytes of all else. It'll actually read the full stripe, modify it so that those zeros are replaced with L's. Then it'll recompute the parity because it's definitely changed. And then it'll write out the full amount. So that 4 kilobyte write became a 32 kilobyte read, then like 44 kilobyte write, spread across like 11 different drives. Another reason is historically, Ceph has defaulted to Erasure as the erasure coding plugin ever since it was first introduced in May 2014. But oddly enough, that same year, that library ended up going into an unmaintained status. It also doesn't take advantage of some of the newer processor features like vector instructions, so like ABX2, ABX512. So here's kind of like some benchmarks showing the different erasure code profiles you might use, and kind of like what kind of throughput you're able to achieve on an EPIC 9354 that I did this testing on. So still pretty reasonable, but ideally you want to use your resources the best you can. So if you could switch to a different erasure coding algorithm, that would be good. And there just happens to be one that Intel created. So this actually was added to Ceph 2 months after Erasure was added. So in July of 2014, this was actually contributed by CERN. So it was a community addition to Ceph instead of developed upstream. It uses Intel's Intelligent Storage Acceleration Library. So this takes advantage of the SIMD instructions that are actually on the processor to, basically double the throughput that you're able to achieve on all the different erasure codes across the board. So good improvement. Starting with Tentacle, this is now the default. But if you deployed your cluster with anything previously and you didn't modify this, you're most likely using Erasure. So switching to ISA is going to give you a good boost. It'll reduce your latencies and increase your throughput using less CPU cycles. ISAL, while it was developed by Intel, it's actually cross-platform. There's actually vector instructions for ARM servers, for PowerPC, and RISC-V was recently added, although it's not in Ceph yet. So those graphs that I created, I actually used the internal benchmarking tool. So this actually isn't taking into account how fast your drives are. It's actually just doing the computations. So this is kind of like instructions on how you can do this benchmark yourself. This is the easiest way I found, is just start up a Ceph ADM shell, install the Ceph test package for whatever environment you're using. So if you're using Tentacle 20.2.4, you would switch it here. If you're using ARM, you would update the architecture here and here. It does, to get good results, you do need to use the Tentacle version. Previous versions only worked on a small 1 megabyte object in memory. So it was it completed very quickly, but the results weren't very consistent. So it's actually a little bit better. This new one, it'll work. What it does is it creates an 80 megabyte chunk of memory, and then it runs through the erasure codes on that 80 megabytes 100 times, and then it spits out 2 numbers. One is the number of seconds it took, and then the number of kilobytes actually encoded. So to calculate what your throughput is, you take the number, like how much data was actually written. So 8 gigabytes essentially. Convert it back over to like, well, convert it to megabytes and then divide it by the number of seconds that it actually took to complete. So here's some of the FastEC benefits. So one of the things that you can do is, or what it does, is it does partial reads. So when you are requesting like a small part of a stripe, it only reads what's needed and not the full stripe. So, if you only want to read Ks, you just read Ks from this OSD. So the other 7 OSDs aren't involved, like, well, except for the primary, which is going to redirect it directly to that OSD. So that's a good improvement, and that actually doesn't need, as far as I know, it doesn't need any thing to be enabled. This is just you upgrade Tentacle and it starts using partial reads. But to enable some of the other benefits on the right side, you run this command. So you enable it on a per pool basis with allow EC optimizations to true. But once it's enabled, it can't be disabled. So if you start running into problems, which we haven't really seen, but also hasn't been tested like in a large production scale. So there might still be some issues that pop up, like the original 0.0 release of Tentacle, I believe had some issues. So one of the big improvements of FastEC is space efficiency. So you're no longer having to pad in like partial shards or partial stripes. That's the correct term. So there's no more padding. So that's a good benefit. And here's kind of like a demonstration of how bad that padding could actually be. So this is on a customer cluster that we kind of graphed like each pool, like every PG. So this kind of like each color is a different pool, and it shows you that this like gray area here is actually just overhead. So in this OSD 22, there's actually 5 terabytes or TB bytes that are being used up just in overhead because of that write amplification, and that's like out of only 9.13 TB bytes. So over 50% of their data is just being used up by overhead. So not using that padding is going to be great, and a lot less wasted space. So partial writes. So this is kind of like an improvement on the read modify write, but it becomes more of a partial read modify partial write. So the read, you only read what is not changing. So like say if we're going to be changing this 4 kilobytes of A's to say 4 kilobytes of Z's, we need to read the other 7 I don't know, stripes or whatever, and then we modify it to Z's, and then we only need to write, well, I guess there's a recompute. We have to recompute the erasure again, but we only need to write what changed. We no longer have to write B's over B's again or C's over C's. We only have to write the Z's and then the new updated parity. So that was a good improvement. And then I also had something called parity delta writes. So it's kind of like a modification of partial writes where, let's see, the substrate write starts with, okay, so it only needs to read what's changing, so the A's, and then the parity. So instead of reading like from these 7 OSDs, you actually are reading the parity and what it started with. And that's so that you can know that like what data changed, and you can actually just recompute the parity data knowing what it was originally and what it changed to. You don't need to know all the parts of the stripe. So that's kind of like a decent improvement as well. And then you only write what changed again, so the parity information and the writes. So here's kind of like a comparison of historically what erasure coding did on like say a 4 kilobyte write. So you would on a read operation it would read from 8 different OSDs. Write, it would write to 11 because of the extra parity bits, and then so the total operations would be 19. With partial rates, you only have to read 7 now. You're writing 4, so it's a 42% improvement. And then with parity delta rates, this is like the biggest change in the number of operations that need to be done. So it's actually a 58% drop. So here's some of the kind of the benchmark results, which we were doing with RBD. Some of it has been kind of like inconsistent, and we need to kind of dig into. But this is on a cluster with like 900 OSDs with hybrid drives. So it has like, what does it have? It had like 30 drives per server, and then like I think it was like 4 WallDB drives that were on NVMe drives. So this is kind of like what I'd expect, because what we're doing is we're doing like a single thread at a time. So this is kind of like reflects like the speed of I don't know what a hard drive would be. So a hard drive writing 1 kilobyte random writes going to be doing a ton of seeks, so you're going to be getting 70 to 80 IOPS. But oddly enough, during this test, the 8+3 FastEC was actually faster than the 3x replica. So I don't quite understand why that is yet. So we're still digging into it. But like the bigger change was on a 4 kilobyte write. All of a sudden, 3x replica jumped a lot. So this is like 900 operations per second. That doesn't work with like hard drives, just because of just how many seeks there are. So I don't really quite understand why it jumped so much. But these both stayed about the same. Like, what was it? 55 went to 65, and 82 went to 93. But then also when you went up to like 32 kilobytes, which is like a full stripe write on that. So because 8 times 4 kilobytes is going to be 32 kilobytes. They all see really good, performance numbers. You don't see a huge improvement from FastEC here, because the main improvements with FastEC is doing partial reads and partial writes. But this is going to be like a full stripe read and full stripe write. Well, technically it's just a full stripe write, because that's all I was testing here. But if you want to try to reproduce these results, we were using the RBD bench tool. Key thing here is you have to disable RBD cache, otherwise you're just going to be testing memory on your client. But you want to see what the cluster actually can do. This is the example of doing it with 1 kilobyte writes, 1 IO thread, and then doing a random pattern is good, because if you do sequential, the drives are going to start combining those writes together and doing much larger rates and kind of skewing your results. How much total data to like write, what pool to use, and like what RBD volume to use. One of the other improvements that they've noticed is if you use a larger stripe, like say like 16 kilobytes for the stripe unit, which ends up like an 8+3 would be just about 128 kilobytes per whole stripe width. This actually improves performance while also like it's like a good compromise between added performance and lower capacity needs. You wouldn't want to do this, stay with like the old erasure coding, because that would add so much more overhead, because the stripe unit, just because the stripe width would be like, so much bigger. You'd say if you wrote 4 kilobytes, it would need 128 kilobytes, or actually a little bit more because of the parity. But some workloads could actually benefit from like even a larger stripe unit of say like 256 kilobytes. Like say if you were writing large, like I don't know, image files or something like that, you would want to take advantage of reads always hitting like 1 OSD at a time instead of being spread across multiple OSDs. So here's some of the things that it like would unlock. It does provide higher performance on RBD and Ceph. So RBD would be like your virtual machine workloads. Ceph, like say if you're running like a large hosting site, like lots of customer sites or whatever, average object size is probably pretty low, like 8 kilobytes or so. but you would take advantage of not needing to write as much. Like there wouldn't be so much overhead. So, and it would also like those 8 kilobytes, like with the 16K stripe unit, would all be served by one OSD instead of spread across like 8 OSDs like it would be with the traditional Erasure coding. Lower space amplification, so that's always good when the prices of drives these days, and reduce network overhead. So this one's not entirely obvious at first, but I've also seen workloads where they were storing like a whole bunch of 64 megabyte objects across the cluster. But they were doing like partial reads of like the same object, like 4 kilobytes here, 4 kilobytes like in a different spot, like a whole bunch of those. But that was like amplifying, like each read was amplified by like 8x, and it was basically saturating their network because that like just it got amplified so much. So this would drastically cut down on like the amount of like network overhead that you would need. So things that it doesn't unlock, you still can't store OMAP data on a Erasure coded pool. So still going to need a replica pool for the OMAP data. It's not reversible, so make sure you do plenty of testing before you start using it. You can't change your stripe unit automatically, so you're going to have to like do like a data migration at any time you want to use a new stripe unit. And it's still going to be a manual switch from JErasure to ISAL. But here's some ideas if you do want to start migrating your data over to FastEC pool. With RBD, Reef added a live migration feature. So you could just, I think there was like a prepare, initiate, and like, I don't remember exactly what it is, but here's like a kind of a blog post on how you could like migrate one RBD volume at a time live to a new pool. So that's actually pretty cool. Also, like say with RBD, there's usually features like say like an OpenStack that take advantage of their own internal way of doing block migration. On a Rails gateway, you can use storage classes with a lifecycle policy. So you can say set up a storage class to like point to your new pool. So you can just set that like on like a bucket, and like any new uploads will go to that pool. But then you can set up a lifecycle policy. So you could be like, anytime the lifecycle policy runs, you could like say migrate it to this pool. So like say after it's a month old, migrate the data to this new pool. Maybe you would want to like if you have a lot of data, maybe you'd want to start off with like if it's older than a year, just move it, and then say if it's older than 11 months, so that way your lifecycle policy processing doesn't take forever. I did do a talk on compression called Switching Squids in Raleigh, North Carolina. The talks here, I go over kind of like the details on how you should use storage classes. On Cephfs, you can actually have different pools backing your Cephfs file system by setting the Ceph dir layout extended attribute on the directories. So this would be an example of setting it to tell any new writes to go to this Erasure coded FastEC pool. This would be like for your whole file system. You could do it on like a per directory basis. And then once you set it, new writes would go to that pool, but your existing data, maybe you want to move it over as well. So what you could do is, the trick I've used is I just make a copy of the file with like the same file name, but with an extension like EC83 FastEC. And then I move that file over the original, which essentially deletes the original. So the data stays the same, but now it's on the new pool. So you could probably do it with like a find command. Like I would probably start off with like anything older than a month, just migrate it, because anything newer is probably being touched a lot more often, because there is like a very short time period where maybe the file could change, like, and then you would be writing old data over the original. So the recommendations I have is stop using JErasure. It's no longer maintained. Switch to ISAL. Benefit is it is maintained and it's faster. Perform benchmarks on your workload because that's what really matters. Switch to using a larger stripe unit with FastEC because it's no longer wasting space, and you could actually reduce small IOs down to like a single drive access instead of needing, all of them. And wait until benchmarks prove that it's faster for you too. So still need to dig into that. Hopefully be able to do like maybe another talk on this at like a Ceph days with like some updated benchmarks for you guys, or maybe we do like a report on our website or something. And I think that's it. So we could open it up for questions.
Awesome. Thank you so much, Brian. So we have some questions already like come through in the Q&A box. So let's jump to those now. So the first one is, it's from Nikhil. He's asking, is modifying the ratio coding algorithm an online change?
So you can't really change the ratio coding algorithm on an existing pool. So you basically have to create a new pool and then migrate your data over.
Okay, perfect. The second question is from Joel. How was the overhead padding on OSDs measured? He has mentioned it was shown on slide 22.
Okay. Okay, so this was kind of measured by like, looking at each placement group, looking at the size of it. Ceph PGLS will show you the size of the placement group, and then dividing by the K value to determine how much actually landed on that OSD. And then, kind of adding up all of those for all the placement groups, and then subtracting that from how much data is actually being used by that OSD. So like 9 terabytes was being used by the OSD, but if you added up all the like per placement groups data, it only added up to, what would that be, like 4 terabytes? So that's how this was figured out. This whole thing was like kind of like vibe coded by Claude, but it's a cool way to view a cluster to see how data is being spread about.
Okay, I hope this answers your question. There's one more from Nikhil. He asked, so does RGW compression or blue store compression have any impact for the performance of FastEC?
I would say it would probably still, have an impact because, you're writing less data to the cluster. Oh, if you're doing blue store compression, it doesn't really change much because that's being done on the OSD level, like after it's already been sharded. But if you're doing compression, like say on the RGWs themselves, the data that you're writing is going to be smaller. So you might be using, less data in, well, the objects you're writing are going to be smaller. So with the padding, you'll get the benefit there. But I don't know if you'll get too much more improvement. Mainly, you'll be reading less data off the cluster. You won't have to do full strict reads. So it'll be slightly faster, but probably wouldn't notice too much.
Okay, I hope that answers your question, Nikhil. Do we have any more questions? Feel free to put those in the chat box. We also have a Q&A box that we can use to put the questions in. Okay, there's one from Nathan. How are parity bits recalculated without rereading the entire object back?
That is a good question that I don't really know the answer to. I just know that it's you could basically use the data that was there before, kind of like, I don't know how you do that exactly, but
it's just
there's some information.
Oh, sorry. Oh, should I have been? I'm sorry to interrupt.
Go ahead, Dan.
It's like exclusive OR. It's like it's a reversible operation. You can just it goes back and forth.
Yep.
The first parity bit, and then for the other, that's the magic of the Galois fields and stuff. All of the parity, there's like a magical mathematical operation that you can just like flip the bits and then apply the same mask to it again, and they flip back to where they were. So you can do just the data chunk and the parity chunks. Yeah. Sorry to jump in. Yeah.
Okay, no problem. Thanks. So that's why you have to read what the data was there before you modify it, is because you need to reverse it before you could apply the new one.
Awesome. I hope that answered your question, Nathan. Okay, so we have one from Gregory. I didn't quite catch the way you calculated that space efficiency. Is it written down somewhere?
No, but it can be. Not sure where to write it down at. But yeah, it's basically, you can actually see this in your Ceph OSD DF output. You could see like, well, it could be. I know there's a way to like, it shows you the like amount of data used versus like what's actually in there. Let me look at the cluster I have right now. Yeah, so if you do a Ceph OSD DF, there's like a data area and a raw used area. And those are usually about the same. Yeah, at least in my cluster they are. It does get a little skewed with if you have like hybrid OSDs where it's like you have the WallDB on an SSD. It's because the SSD right now, like whatever is used for the WallDB partition is just automatically added to the total size of an OSD. Like it shows up as used like right away. So it's really kind of confusing. But also increases the total size of the drive too when you, especially if you have like a very large WallDB partition. But yeah, look at Ceph OSD DF output, compare data like stored versus raw used on each drive.
Okay. We have one more question. This is from Gustavo. In your tests, which stripe size did you use for the non-enabled FastEC?
For those tests, I just stayed with 4 kilobytes. So it was 4 kilobytes for all 3 of these.
Okay. I hope that answers your question. Do we have any more questions? So to Nathan's question, Dan posted something in the chat box as well, so everyone can take a look at that if you need. Do we have any more questions? No, seems like we don't have any questions. Yep, there's
Cool.
in the Q&A. Okay, that was quick. That was nice. So yeah, Bryan, do you want to add any final notes?
Yeah, I hope you guys learned something today because I definitely learned stuff creating it for you guys.
Awesome. So thank you so much, everyone, for spending this time with us today. We really appreciate this engagement. Have a wonderful day, everyone. And just so before I wrap up, like I just want to flag that today's session was recorded, and we will be sending the recording to you within a follow-up email. So yeah, keep an eye on your inbox and have an amazing rest of the day.
All right. Thanks, everyone.
Awesome.